Alrighty, chapter 11 is a little bit on the shorter end, pretty easy chapter overall. We'll have 4 total videos to get through the 5 sections of the chapter. This first video is going to look at 11.1 and 11.2 together. Just to put it on your radar, a bulk of the section is centered around 11.4, colligative properties. That's going to be where you want to focus your attention to pull the material out of this chapter. But before we can get to that, we have to get a little bit of background here from 11.1 through 11.3. So in chapter 9, we talked about gases, chapter 10, liquids and solids, right? But it's not exceptionally common that we're dealing with pure substances like that. And so chapter 11 is all about solutions when we have things mixed together, and then colloids, which is something a little bit different we touch on at the end of chapter 11 and 11.5. But before we can get to that, let's talk about 11.1, which is the dissolution process. Yep. You know what a solution is at this point, right? If you go back and check your notes, when we learned a homogeneous mixture, it would say also known as a solution. Yep. And we also introduced the idea of a solute and a solvent. Yep. Thinking about like molarity, for example, right? You're focused on the concentration of a solute in a solvent, okay, to form a solution altogether. The solute gets dissolved into a solvent. Okay? Everything is soluble to a degree. Some things are really soluble, some things are virtually insoluble. Okay? We learned about solubility rules first in chapter 4 to see if something would A, dissolve in water, and B, whether or not it would break apart. But as we'll see by the end of chapter 11, right, you can really have a solution in any state. It doesn't have to be a solid solute going into a liquid solvent, right? Match up any of your different states of matter, right? Solid, liquid, gas, any of those could be a solute in a solid, liquid, or gas solvent, which is kind of weird to think about, right? But they all have a different name. Okay? Some obviously are much more common than others. Okay? But we're starting with just a basic understanding, right? Think about what you think about a solution as, right? Putting sugar into coffee, taking a solid, putting it in a liquid, and they form a solution together, a homogeneous mixture. So what we need to understand about solutions, a lot of this might be background knowledge, but we always want to refresh these things before we continue. Your solutions are homogeneous throughout, meaning they have a uniform composition. Okay? So it doesn't matter where you sample it, top, bottom, left, right, middle, outside, it is the same composition throughout. Everything is the same physical state in that solution because it's uniformly distributed on a molecular scale. Right? They are evenly distributed. Yep. Solutions don't have a solute that will settle out. So it's not like we're mixing something together and calling it a solution, but if we leave it for enough time, then it starts to precipitate out a solution, right? That's not a solution. Okay? That's something else called a suspension. So here, that solute is not going to settle out. Doesn't matter how long we leave it. Okay? And as you know, right, thinking about making Kool-Aid, right, you can vary the composition of a solution to various degrees. It can have a low concentration or it can have a high concentration. You can form solutions in different ways, different molarities. Okay? And the formation of a solution always happens spontaneously. When we're making this solution, it's favored by a decrease in the internal energy of the solution. It's an exothermic process, and it's an increase in disorder, okay? Or entropy is favoring that as well, if you recall some of those from your physics classes. If not, we'll get into some of those ideas later on with thermodynamics. Okay. So what else is going on with solutions? Well, if we have something that's known as an ideal solution, again, this is a thought construct, it doesn't actually exist. Things can approach an ideal solution just like gases can approach an ideal gas. Something we would call an ideal solution forms with no energy change whatsoever. Okay, meaning we formed a solution in the IMF, the intermolecular forces between the solute and the solvent are identical to one another. So say it's hydrogen bonding. Right, we have the same degree of hydrogen bonding as we did in the solute as we do in the solvent. Right? But that's not really going to happen because we've got a bunch of different interactions that are going on. Right? solute-solute, right, the interactions between the solute particles themselves, solvent-solvent, the interactions between the solvent particles, and then when they get introduced to one another, the solute-solvent interaction. Okay? And changes in these IMFs control whether or not something dissolves. Because, for example, if we have really strong solute-solute interactions or really strong solvent-solvent interactions, those things want to stay together. They don't want to get dispersed throughout a solution. So in that case, it won't dissolve and we won't form a solution. If we want to form a solution, we want really good solute-solvent interactions. Yep. So here's an example of what would approach an ideal solution between helium and argon, right? It's fusing through that hole, forming a mixture of the two gases, and we could think about that as being a solution. Okay, it's again favored because the entropy is increasing. Okay? Again, thermodynamics. So this is as close as we would get to an ideal solution. Okay. Now, if we're forcing something to dissolve, we're forcing those interactions, those IMFs, to break apart in order for it to get distributed in the solution. All right, so that's endothermic, interrupting those IMFs. So in order for a solution to spontaneously form, right, the interactions between the solute and the solvent has to be stronger. So that makes it exothermic. Okay? And overall, we have a decrease in internal energy because breaking up the solute particles or the solvent particles, those IMFs is always endothermic, requiring energy. And so we want to release an energy, exothermic, when the solute and the solvent come together. That's how we form a spontaneous solution. Okay? And that process is known as solvation. Make sure you have that jotted down in your notes. But that's why, for example, oil and water don't mix together with one another. Right? If you've been to a diner and seen that dressing on the table, you know that oil and water don't mix, right? You can shake it up and get a suspension, but eventually it's going to settle back out because, right, if we think about the oil and the water, right, oil interacts really strongly with one another. The water interacts really strongly with itself, but they don't mix together very well. The solute-solvent interactions are weak because oil is nonpolar and water has hydrogen bonding. They're not like one another. So trying to mix them together is overall more endothermic than it is exothermic. So they don't mix. Okay. And this is just kind of, you know, if you're a visual learner, a image of what's happening to form a solution. Right? These things directly form, but if you think about it, right, we've got to break up the solute, break up the solvent, and then mix them together. And so this here, step 2 and step 1, those are endothermic processes. We need them coming together to be exothermic. Thinking, you know, again, just like solubility, like dissolves like. The more similar these things are to one another, the easier time we will have in forming a solution overall. Okay. If we take like a cold pack, for example, ammonium nitrate in water is typically how these cold packs are made up. That's overall, right, forming that solution, you know, you force it to happen, it's an endothermic process. It's requiring energy, and that's why it feels cold. Okay? Chemical cold pack. So that's 11.1. Let's quickly finish up with 11.2. We need a little background on what I alluded to with electrolytes. Okay? Because we talked about if something will dissolve, but also if it will break up or stay together. And that's where that word electrolyte comes into play, right? We're not thinking just about Gatorade here and the electrolytes that your body needs. So now we're trying to think about the question, what happens when a compound dissolves? Okay. Well, if it yields ions in solution, it's called an electrolyte. And there's two different types of electrolytes. Strong electrolytes break up to give ions 100%, just like a strong acid fully dissociates. Okay. Weak electrolytes just give us a little bit of ions. They do not fully break up in solution, just a fraction. Okay. Non-electrolytes don't produce ions. Now, here's a common area of confusion, right? Both electrolytes and non-electrolytes dissolve in water, okay, or whatever your solvent is in consideration, right? But now we're considering whether or not they produce ions. Okay? So non-electrolytes still dissolve. Like sugar is a non-electrolyte. It dissolves, but it does not produce ions. Whereas, salt, sodium chloride, dissolves, yes, and is also an electrolyte, strong electrolyte. It makes ions in solution, right? Na plus and Cl minus. And that's determined by measuring conductivity. And that's where electrolyte comes from, right? Now, ethanol, for example, dissolves, but it's a non-electrolyte, so it doesn't conduct electricity. Okay. But potassium chloride here, strong electrolyte, fully dissociates. Okay. See how lit up that light bulb is? Acetic acid, vinegar, it dissolves. It's a weak electrolyte. Okay, so it will conduct electricity, yes, but not as much as a strong electrolyte will, because it's those ions in solution that conduct electricity. Strong electrolytes give you a lot of ions, weak electrolytes, only a handful. So why are these things dissolving and breaking up? And this ties into chapter 10. It's one new form of intermolecular force. And we had dipole-dipole before. Now we're thinking about ion dipole attractions. It's an electrostatic attraction between an ion and some sort of molecule that has a permanent dipole. Okay. So water, we know, right? HOH has a large delta positive on hydrogen, a large delta negative on oxygen. And so it has a permanent dipole on water. And therefore, those partial charges, partial positives or partial negatives, will interact strongly with an ion of the opposite charge. That reduces the electrostatic forces between the ions, thinking about this solvation process, and spreads them out throughout the solution. Okay? So that's known as dissociation. Electrolytes dissolve, yes, but so do non-electrolytes. What's unique to electrolytes is the fact that they don't only dissolve, but they dissociate. The individual ions break apart from one another. And here's what that looks like. Okay. Take potassium chloride. Your K plus, your positive charge, right, is surrounded by the delta negative on oxygen, which is red in this case. Your chloride, your Cl minus, is surrounded by hydrogen, that large delta positive on hydrogen. Okay, so that's solvation, and we see that those ions here in KCl are dissociating. Okay. Keeping in mind that that doesn't occur for everything that's ionic. Right? There's different forces in consideration. That's why not everything is soluble. Okay. There's also something known as a covalent electrolytes. Covalent electrolyte, those aren't as common as ionic electrolytes. And those only exist where something reacts with water specifically to produce an ion in solution. Okay. So those are mentioned in your textbook. Don't worry, as much of those for quiz or exam time. Just have it on your radar that they exist. Our focus here is for ionic electrolytes. So know those properties of solutions, know the difference between an electrolyte and a non-electrolyte, specifically strong and weak electrolytes. And then we'll use those in the next video to talk about solubility.